So here's a question that literally every single one of us will eventually have an answer to. What really happens to your body when you die? And I'm not talking about the philosophical or spiritual aspect, though we will touch on some fascinating near-death experiences later. I'm talking about the actual anatomical and physiological cascade of events that occurs in your body during the process of dying and in the hours after death. Because your body doesn't just turn off like flipping a light switch. There's a whole sequence of events that happens, some of which are extremely fascinating. So today, we're gonna cover these events, talk about what we do know, what we don't know, and as I already hinted, touch on some of the unexplainable events at the end. It's going to be a departed one. So let's jump into this anatomical and physiological awesomeness. So let's start with what happens in the moments leading up to death. Now, obviously, death can occur in many different ways: cardiac arrest, trauma, illness, cancer. But regardless of the exact cause, there's a common pathway the body follows once certain critical systems begin to fail. And so let's use cardiac arrest as the primary example, since it's one of the most studied scenarios. When your heart stops beating, blood is no longer being pumped throughout your body. Remember, blood is delivering oxygen and nutrients to all of your cells, particularly to that very demanding organ sitting inside your skull, the human brain. Within about 15 to 20 seconds of your heart stopping, you lose consciousness. This happens because your brain, which makes up only about 2% of your body weight, but uses roughly 20% of your oxygen supply, is immediately starved of that oxygenated blood. The neurons in your cerebral cortex, the outer portion of the brain responsible for consciousness, thought, and awareness, starts to shut down almost immediately. But here's where things get interesting. Even though you're unconscious and your heart is stopped, your brain does not instantly die. In fact, research shows that measurable brain activity can persist for a short period of time after the heart stops beating. Several studies have documented organized electrical activity in the brain for minutes following cardiac arrest. In some cases, EEG recordings have shown brain waves continuing for up to 10 minutes, although this activity rapidly becomes weaker and more disorganized over time. A 2023 study published in the Proceedings of the National Academy of Sciences observed a brief surge of gamma wave activity at the moment of death in a small number of patients after life support was withdrawn. Gamma waves are often associated with processes like memory retrieval, information integration, and conscious awareness. However, it's important to note, seeing gamma activity does not necessarily mean a person is consciously experiencing these events. It simply shows that certain neural networks can become briefly active during the dying process. But how is it possible for brain activity to continue at all after the heart stops? Well, one reason is that neurons don't run out of energy instantaneously. While neurons do not store energy in large reserves, they do contain very small, rapidly turning over amounts of ATP that are already in use at the moment circulation stops. Neurons also contain a small amount of phosphocreatine, which can briefly buffer ATP levels for a few seconds when energy demand suddenly spikes. In addition, neurons can temporarily rely on anaerobic energy pathways, such as glycolysis, that do not require oxygen. Also, supporting cells in the brain called astrocytes store small amounts of glycogen, which can be broken down into lactate and shuttled into neurons as an emergency fuel source when blood flow is lost. However, all of these backup systems are extremely limited. Without oxygenated blood, mitochondrial ATP production rapidly collapses. Ion gradients across neuronal membranes fail, and normal electrical signals break down within minutes, which is why prolonged cardiac arrest leads to irreversible brain injury and death if blood flow and oxygen is not quickly restored. But these short-lived energy buffers may help explain why organized brain activity can briefly persist after the heart stops, and they may also contribute to some of the vivid experiences people report during near-death states, which again, we'll talk about in more detail later on. Now, while your brain is going through this process, the rest of your body's cells are also beginning to die, but at different rates. Your brain cells are kind of the divas of the human body. Neurons begin to suffer irreversible injury within about 4 to 6 minutes without oxygen, but other cells are more resilient. This is because many of these cells have larger glycogen reserves, lower overall energy demands, and a greater ability to rely on anaerobic metabolism when oxygen is no longer available. Skin cells, for example, can survive for several hours after death. And believe it or not, some cells in the body can remain metabolically active for days. In fact, studies have shown that gene activity in certain cells, such as certain white blood cells and muscle satellite cells, can still be detected up to about 96 hours after death. But just like the neurons, these cells eventually reach a point where they can no longer generate enough ATP to maintain normal function. Ion pumps begin to fail, calcium floods into the cell, destructive enzymes are released, and the cell essentially begins to digest itself from the inside, a process known as autolysis. During this dying process, there are also physical signs that medical providers look for. The skin may become pale or take on a bluish tint, especially in the extremities due to the lack of oxygenated blood, and this is called cyanosis. Breathing patterns may also change dramatically, and in some cases, providers observe a pattern called Cheyne-Stokes respirations, where breathing becomes irregular, with periods of rapid breathing followed by periods of no breathing at all. Body temperature begins to drop, though interestingly, in some cases there can be a brief spike in temperature shortly before death. The pupils of the eyes become fixed and dilated because the muscles controlling them are no longer receiving signals from the brain. And in many cases, there's a release of urine and stool as the sphincter muscles relax. Not the most distinguished aspect of death, but it's the reality of the physiological process. Now, earlier I mentioned that phosphocreatine can help buffer ATP supply when a neuron is starved for oxygen during the process of dying. And we do know that creatine supplementation can increase your stores of phosphocreatine. Now, I'm not suggesting that we supplement with creatine to possibly increase neuronal activity for a few more seconds during the dying process, because there are plenty of other reasons and benefits to supplement with creatine while you're still alive. And that's why I want to take a second to say thank you to the sponsor of today's video, Create. These guys created the first creatine monohydrate gummy, and they are made using the highest quality of CreaPure creatine monohydrate, which has been third-party tested for quality. Plus, they taste great, as they come in multiple flavors like blue raspberry, sour green apple, and my personal favorite, sour peach. One of my favorite things about these gummies is how convenient they are. No need to mix it in with a drink or shake. You can just pop a few of them into your oral cavity and chew them up, which I especially love when I go out of town or when I'm on the go. I no longer have to pack a whole bottle of creatine or transfer powder into a little Ziploc bag. Creatine is one of the most well-studied supplements, and I find very few reasons for people not to be supplementing with creatine. Because yes, it clearly helps improve exercise performance, but it also can improve cognitive function and even help with sleep deprivation. So if there's a high-quality creatine product like Create, I can definitely support that. So if you're interested, go to trycreate.co/humananatomy and use our code HUMANANATOMY to get 30% off. That link will also be in the description below. And now, let's get back to what happens after we die. Okay, so let's say someone has been declared dead. The heart has stopped, the person is no longer breathing, and there's no brain activity. What happens to the body in the hours immediately following death? Well, first up is something called Algor mortis, which is just a fancy Latin term for the cooling of the body. Your body normally maintains a temperature of around 98.6 degrees Fahrenheit or 37 degrees Celsius due to ongoing metabolic processes. But once these processes stop, your body begins to equilibrate with the ambient temperature around it. Early on, the body is estimated to cool at roughly 1 to 1.5 degrees Fahrenheit per hour, though this rate is not constant and can vary widely based on factors like the person's body composition, what they're wearing, air movement, and the surrounding environmental temperature. This is actually one of the methods forensic scientists use to help estimate time of death, but it's considered an approximate tool rather than a precise measurement because of all of these variables. And next is livor mortis, also called lividity. Remember, your heart is no longer pumping blood through your vessels, so gravity takes over and blood begins to pool in the lowest parts of the body. If someone dies lying on their back, you'll see a purple to reddish discoloration on the back of the body, the buttocks, and the backs of the legs, where the blood is starting to settle. This process typically begins within about 20 minutes to a few hours after death and gradually becomes fixed over time, often by about 8 to 12 hours depending on conditions. Fixed means that if you press on the skin, the discoloration won't blanch, and it will no longer shift to a new location if the body is repositioned. This phenomenon is also used in forensic investigations, because if a body shows lividity in areas that don't match how the body was found, it suggests that the body was moved after death. Then we have probably the most well-known postmortem change, rigor mortis, the stiffening of the body. This happens because of what's going on at the cellular level inside the muscles. Remember how the cells lose their ability to produce ATP after death? Well, ATP is actually required for muscle relaxation, not just for contraction. When a muscle contracts, little protein filaments called actin and myosin bind together. To unbind them and relax the muscle, you need ATP. But after death, there's no ATP being produced. So initially, for the first few hours after death, muscles are actually relaxed because there's still some residual ATP present. This phase is actually called primary flaccidity, but as that ATP gets used up, the actin and myosin filaments become locked together, and the muscles become rigid. Rigor mortis typically begins in the smaller muscles of the face, neck, and hands within about 2 to 6 hours after death, and then progresses to the larger muscles of the body. The body generally reaches maximum rigidity at about 12 to 24 hours after death, depending on conditions. Then interestingly, rigor mortis reverses. After roughly 24 to 48 hours, ongoing autolysis and bacterial decomposition causes muscle proteins, including actin and myosin, to break down, which causes the protein bonds to dissolve and the muscles begin to relax. This phase is referred to as secondary flaccidity. And there are obviously other changes happening as well. The corneas of the eyes become cloudy within a couple of hours after death because the cells that normally pump fluid out of the cornea stop functioning, leading to dehydration and swelling. And if the eyes are open, this clouding can happen even faster due to evaporation. The skin also begins to take on a marbled appearance, known as marbling, which occurs as red blood cells break down and bacteria spread along the superficial blood vessels during early decomposition, creating a blanching, purplish pattern beneath the skin. And even though it may not be obvious on the outside, decomposition is already beginning at the cellular level within minutes of death, as cells undergo autolysis and start to break down from the inside. The more dramatic, visible signs of decomposition, however, take longer to develop. But also, there's this bacteria that lives inside you, especially in your gut, like in the intestines. And this bacteria will start to break down tissues and produce gases as a byproduct. This process, known as putrefaction, sets the stage for bloating and other visible changes that typically develop over the next 1 to several days, again, depending on environmental factors. But now, let's shift gears and talk about something that's absolutely fascinating, and frankly, still pretty mysterious from a scientific standpoint: near-death experiences, or NDEs. Near-death experiences are often life-changing, profound psychological events that occur when someone is close to death or in situations where death seems imminent. These can occur during cardiac arrest, severe trauma, under anesthesia, or even in situations where someone thinks they're about to die but are not actually in any physical danger. And here's the thing that makes NDEs so interesting. While they are not identical, many near-death experiences share many recurring themes across different cultures, ages, and backgrounds. People from completely different parts of the world, different religions, and different time periods often describe experiences with overlapping features. And even though the exact details can vary, it's this pattern of shared themes that has researchers so intrigued. Research by Dr. Bruce Grayson and others has identified several core features of near-death experiences. Not everyone experiences all of these features, but one of the most frequently reported features is an out-of-body experience. People describe a sensation of separating from their physical body and viewing it from an outside perspective, often from above. Some people report perceptions that later appear to match specific events that occurred during their resuscitation. And as you can imagine, the timing and mechanisms behind what's causing these perceptions remains an area of active scientific debate. Dr. Sam Perina's AWARE study found that about 40% of cardiac arrest survivors who were successfully resuscitated reported some form of recalled experience during their cardiac arrest, although many of these experiences were fragmented or nonspecific, and only a small number involved structured awareness. It's also important to note that clinically dead, in this context, refers to the absence of a detectable pulse, not necessarily confirmed absence of all brain activity. Around 30% of people who have NDEs also report moving through some kind of tunnel or dark space. This is often described as moving toward a light, sometimes rapidly and sometimes with a sensation of flying. The light is often described as brilliant, warm, loving, and unlike any earthly light. And many people describe it as having a presence or a personality. Plus, in positive NDEs, about 80% of people report an overwhelming sense of peace, contentment, and unconditional love, with many saying they didn't want to return to their physical body. But there are a small percentage of NDEs that can be distressing instead of positive. But many people also report encountering other beings, often deceased loved ones, and the identities of these beings frequently aligns with a person's cultural and religious background. Some people experience a rapid replay of significant life events, often from multiple perspectives, and some describe reaching a boundary that they understand they cannot cross if they want to return back to life. So what is actually happening during these experiences? Well, as we've learned today, we know the brain doesn't instantly shut down. We know brain activity can briefly persist, and in rare cases show transient surges after cardiac arrest, though this activity typically declines rapidly. We know certain neurochemicals are released, and much of this could possibly explain what is happening during near-death experiences. But we don't know how to fully explain detailed, coherent experiences or precisely when they occur, especially during periods when brain activity is expected to be severely impaired. We don't know how some people report perceptions that later appear accurate during periods of presumed unconsciousness, particularly given the limitations of EEG and other monitoring methods. And we don't know why these experiences show recurring themes across many cultures and time periods. So yes, physiologically, we do know quite a bit about what happens as a person dies. The heart stops, consciousness fades within seconds, brain cells begin dying within minutes, and the body undergoes predictable changes over the following hours. But what happens to consciousness, to that sense of you, remains a very interesting question. And whether near-death experiences represent consciousness beyond the brain and this life, or whether they reflect the brain's final neurological activity, these experiences continue to challenge what we think we know about what happens after we die. And maybe that's okay. Maybe some questions are meant to keep us wondering, or at least keep us wondering until that moment when each of us finds out for ourselves.